Just over 100 light years from Earth, around a star too faint to see without a telescope, astronomers spent years searching for something they had strong theoretical reasons to expect existed, but had never actually seen. Not a signal, not an indirect shadow flickering across a distant star's light. An actual, direct photograph of a planet itself, sitting exactly where the physics said a young planetary system should be quietly building one. In June of 2025, that search finally succeeded, and it succeeded using a method so difficult that astronomers have relied on it for barely a fraction of the nearly 6,000 exoplanets discovered to date. This is the story of TWA-7b, the first new planet the James Webb Space Telescope has ever found by simply looking at it directly, and why doing exactly that turned out to be one of the hardest things in modern astronomy. To understand why capturing a direct image of a planet outside our solar system counts as such a significant achievement, you first have to understand just how overwhelmingly difficult that specific task actually is, and why nearly every other exoplanet ever discovered was found using an entirely different, much less direct approach. Since the first confirmed detection of a planet orbiting a sun-like star back in 1995, astronomers have identified nearly 6,000 exoplanets. The overwhelming majority of those discoveries didn't come from anyone actually seeing the planet itself. They came from indirect methods, clever workarounds built specifically to get around the fact that planets are extraordinarily faint and extraordinarily close, from our vantage point to the blazing stars they orbit. The most common technique, known as the transit method, watches for the tiny, precise dimming that occurs when a planet passes directly in front of its star from our line of sight, blocking a small fraction of that star's light for a few hours at a time. Another common approach, the radial velocity method, measures the subtle gravitational wobble a planet's own gravity induces in its host star as the two objects orbit their shared center of mass. Both techniques have been extraordinarily productive, responsible for the vast majority of exoplanet discoveries made over the past 3 decades, but neither one actually shows you the planet. Both methods infer a planet's existence from the effect it has on its star, the way you might infer a person is standing behind a curtain by watching the curtain move, without ever actually seeing the person themselves. Direct imaging, capturing an actual photograph of a planet's own light, whether reflected starlight or the planet's own residual heat glowing in infrared, is a fundamentally different and vastly more difficult challenge. Anne-Marie Lagrange, an astrophysicist at the French National Center for Scientific Research and the lead author of the eventual TWA-7b discovery paper, described the core problem in remarkably simple terms in comments reported by Science News following the discovery's publication. The star is bright and the planet is very faint. That simplicity hides an enormous technical challenge. A star can easily outshine an orbiting planet by a factor of many millions, sometimes billions, depending on the wavelength of light being observed and the specific properties of the star and planet involved. Attempting to photograph a planet directly is a bit like trying to photograph a firefly hovering a few inches away from the beam of a lighthouse from many miles offshore, while that lighthouse beam is actively pointed directly at your camera. The firefly's own faint glow is real and technically detectable in principle, but it's drowned out almost completely by the sheer, overwhelming brightness of the light source sitting immediately next to it. Because of that fundamental difficulty, direct imaging has historically accounted for only a small fraction of confirmed exoplanet discoveries, and it has generally only worked for very specific, favorable situations. Young planets, still glowing with residual heat left over from their formation, orbiting relatively far from their host stars, where there's enough physical separation in the sky to attempt to block out the star's light and still see the planet sitting nearby. Even under those favorable conditions, it took the combination of an extraordinarily sensitive telescope and a very specific piece of engineering to make new discoveries, through direct imaging a realistic possibility. That piece of engineering is called a coronagraph, and it's central to how this discovery actually happened. A coronagraph is, at its core, a carefully designed instrument built to physically block out the light coming from a bright central object, in this case a star, while still allowing much fainter light from nearby objects to reach the telescope's detectors relatively unobstructed. The concept isn't new. Astronomers have used coronagraphs in various forms for decades, including to study the sun's own faint outer atmosphere, or corona, during observations here on Earth, which is where the instrument gets its name. But building a coronagraph precise enough to suppress a distant star's light by a factor of millions, while still preserving extremely faint signals from an object sitting almost immediately next to that star in the sky, requires an extraordinary level of optical precision that wasn't really achievable for searching out new, previously unknown exoplanets, until an instrument like the James Webb Space Telescope came online. The specific instrument responsible for the TWA-7b discovery was a coronagraph built into Webb's mid-infrared instrument, commonly abbreviated as MIRI, one of 4 primary science instruments carried aboard the observatory. According to the French research center CNRS, which led the study, This particular coronagraph was a French-produced component, integrated directly into MIRI's broader design, specifically engineered to suppress starlight with the kind of precision necessary to hunt for exactly this sort of extremely faint, closely positioned signal. The target of the search was a young star called TWA7, sometimes also referred to by the designation CE Antlii, located roughly 111 light-years from Earth. TWA7 belongs to a loose grouping of young stars astronomers called the TW Hydrae Association, a collection of stars that are all, by astronomical standards, still quite youthful, generally estimated to be somewhere around 10 million years old, a tiny fraction of our own sun's roughly 4.5 billion year age. That youth mattered enormously to the search. Young stars are frequently still surrounded by what astronomers call a debris disk, a broad, flattened ring of dust, small rocky fragments, and icy particles left over from the same collapsing cloud of gas that formed the star itself, material that hasn't yet fully coalesced into planets, or that represents the leftover debris from planets that have already formed, still settling into a stable, orbital configuration. TWA7 has exactly this kind of debris disk, one that had already been studied and mapped in earlier observations, revealing a series of distinct concentric rings, along with subtle irregularities in those rings, such as narrow gaps and slightly asymmetric structures, the kind of features that often hint, indirectly, at the gravitational influence of a planet quietly orbiting somewhere within or near the disk, shepherding the surrounding material into place the way a planet's gravity can carve visible gaps into a ring system. That's precisely why TWA7 became a specific, deliberate target for this kind of search, rather than an entirely random star chosen at will. Lagrange and her research team had good theoretical reason to suspect a planet might be hiding somewhere within that structured, gapped debris disk, based on exactly the kind of gravitational sculpting patterns that planets are known to produce in similar systems elsewhere. What they didn't have, before turning Webb's coronagraph toward the system, was direct visual confirmation. Using MIRI's coronagraph to suppress the overwhelming glare of TWA7 itself, and then applying advanced image processing techniques to further filter out whatever residual starlight still managed to leak through the instrument's suppression, the research team's data revealed a faint, distinct source of infrared light sitting within the debris disk, in a location consistent with exactly the kind of gap-carving influence the disk's earlier structural features had already hinted at. Follow-up analysis, described in the team's paper published in Nature on June 25, 2025, indicated the object had a mass roughly comparable to Saturn, or somewhere in the neighborhood of 95 times the mass of Earth, making it, at the time of its discovery, the least massive exoplanet ever confirmed through direct imaging, a genuinely significant technical milestone in its own right, separate from the broader excitement of the discovery itself. That distinction is worth sitting with for a moment, because it gets at exactly why this particular find mattered so much to the broader field of exoplanet science, beyond simply being a new planet added to an already substantial catalog. Historically, direct imaging has been heavily biased toward finding only the largest, most massive, brightest planets, ones with enough residual formation heat and enough physical separation from their host star to be detectable at all using older instruments and techniques. Confirming a planet with a mass similar to Saturn, considerably less massive and less luminous than most of the giant planets previously found through direct imaging, represented meaningful, measurable progress toward eventually being able to directly image planets closer in size to Earth itself. A long-term goal that remains well beyond current technology, but one that every incremental step like this one moves closer to becoming realistic. It's worth being precise about the specific language astronomers have used to describe this result, since getting that framing right matters for understanding exactly what was and wasn't confirmed. Multiple outlets covering the initial announcement, including the Smithsonian Magazine, describe the object as probably an exoplanet, noting that, if confirmed, it would represent the telescope's first direct discovery of a planet outside our solar system, a specific and carefully qualified way of describing a genuinely new find, distinct from Webb's very first exoplanet image, which came years earlier and involved an already known planet rather than a new discovery. That earlier image is worth mentioning directly, both for historical context and because it's frequently and understandably confused with the TWA7b discovery and less careful reporting. In September of 2022, not long after Webb became fully operational, NASA released the telescope's first ever direct image of an exoplanet, a gas giant called HIP 65426b, located roughly 385 light-years from Earth, with a mass somewhere between 6 and 12 times that of Jupiter. That 2022 image was a genuinely important early demonstration of Webb's direct imaging capabilities, showcasing the planet across several different infrared wavelength bands and confirming that the telescope's instruments, including its various coronagraphic modes, worked as designed. But HIPA 65426b wasn't a new discovery in the way TWA7b was. It had already been identified years earlier in 2017 using a ground-based observatory, the Very Large Telescope operated by the European Southern Observatory in Chile. Webb's 2022 image confirmed and expanded scientists' understanding of an already known world, demonstrating the telescope's raw imaging capability in the process. TWA-7b, discovered nearly 3 years later, represented something categorically different. The first time Webb's own observations led directly to the identification of a planet nobody had previously confirmed existed at all. Aaron Carter, a postdoctoral researcher at the University of California, Santa Cruz, who had been involved in analyzing Webb's earlier images of HIP 65426c, offered a comment at the time that, in hindsight, reads almost like a direct prediction of what would eventually happen with TWA-7b. Carter noted that the 2022 result represented only the beginning, expressing confidence that many more exoplanet images were still to come, images that would continue shaping scientific understanding of planetary physics, chemistry, and formation, and specifically raise the possibility that Webb might eventually help discover previously unknown planets as well, not merely reimage ones already found through other methods. That prediction, made in 2022, was borne out almost exactly 3 years later. There's a broader scientific significance to finding a planet specifically within a young star's debris disk that's worth explaining clearly, because it connects this single discovery to one of the biggest open questions in planetary science: how do planetary systems, including our own, actually form in the first place? Stars form when a large, cold cloud of gas and dust collapses under its own gravity, and as that collapsing material flattens out into a rotating disk around the newly forming star, it's within that same disk that planets are generally believed to form, through the slow accumulation of dust grains into pebbles, pebbles into larger rocky bodies, and eventually larger bodies into full planets. In some cases, pulling in substantial amounts of surrounding gas to become giant planets like Jupiter or Saturn along the way. And because TWA-7 is still relatively young, at roughly 10 million years old, observing a planet caught in the act of shaping and interacting with its own surrounding debris disk offers scientists something considerably more valuable than simply another data point in an exoplanet catalog. It offers a genuine, direct, present-tense window into planet formation and early planetary system evolution, captured at a stage of development that our own solar system passed through roughly 4.5 billion years ago, long before any instrument capable of observing it existed anywhere. The technical achievement underlying all of this deserves its own recognition too, separate from the scientific significance of the discovery itself. Successfully suppressing the light of a star bright enough to overwhelm a nearby planet by a factor of millions, while still preserving a clean enough signal from that faint planet to determine its approximate mass and confirm its physical reality, represents a genuinely difficult engineering and data processing challenge, one that required not just Webb's powerful primary mirror and sensitive infrared detectors, but also the specialized coronagraph hardware built specifically for this kind of observation, and sophisticated post-processing techniques developed and refined by researchers like Lagrange and her collaborating team over years of preparatory work. None of that came together by accident. It represented the culmination of a deliberate, carefully planned observational strategy, targeting a specific star selected because its already known debris disk structure offered strong circumstantial evidence that a planet was likely hiding somewhere within it, waiting for an instrument finally capable of actually seeing it directly. As of June 2025, when the discovery was formally announced, astronomers had confirmed nearly 6,000 exoplanets across the full history of the field, the overwhelming majority found indirectly, through the shadow of a transit or the gravitational wobble of a distant star. TWA-7b, sitting quietly within its young star's debris disk, 111 light-years from Earth, represents something different. A planet astronomers can point to, in a very literal sense, and say they have actually seen, captured not as an inference or a mathematical deduction, but as a faint, hard-won point of infrared light, pulled carefully out from underneath the overwhelming glare of the star it orbits. That distinction between inferring a planet's existence and actually photographing it is really what makes this particular discovery worth understanding on its own terms, without needing any exaggeration to justify the attention it received when it was first announced. Astronomers have spent 3 decades building an extraordinary catalog of exoplanets using clever, indirect methods that remain enormously valuable and continue to drive the overwhelming majority of new discoveries even today. But there's something distinct about a direct image, about starlight from 111 light-years away being deliberately, precisely blocked out just enough to reveal a small, faint, previously unknown world, sitting quietly in the dark beside it, still young enough to be, actively shaping the disk of debris surrounding its own star, doing today, in real time, something very similar to what the planets of our own solar system were doing 4.5 billion years ago, long before anything capable of watching existed anywhere to see it happen. If you want to see what Webb's coronagraphs turn up next as astronomers continue searching nearby young stars for planets exactly like this one, that search is still actively ongoing. Subscribe if you'd like to follow where it leads.